From Utah Public Radio, this is Undisciplined. I'm Matthew LaPlante. Last week on this program, we began a conversation with the zoologist and photographer David Maitland about his new book, which is called The Shape of Nature. And in that interview, Maitland told me that he always wanted to get closer and closer to the things he photographs. And when you do that, you start to notice things that you might not see from a bit further away. Patterns that emerge again and again, albeit originating in different ways across the natural world. Maitland is obsessed with these patterns. But his book isn't just an exploration of that idea. It's a celebration of it and an opportunity to consider how it is that we see the world in the ways that we do. Maitland is an internationally acclaimed nature and science photographer who specializes in small and microscopic forms. And if you listened to last week's episode, you know that he also has a gift for explaining the shapes nature takes and the origins of those patterns.
And I think everybody who's made an IKEA or other, flat pack furniture would know that, the first one that you make so many mistakes and it takes you forever, all day if you're lucky. And then if you've got two of them to make, the second one is like a breeze in comparison. And then if you've got three of them, well, the third one, you're an absolute expert.
And so symmetry is efficient. It's genetically efficient.
Very efficient.
Another common pattern we see across nature, there are many of these in your book, is the spiral. And I didn't know this until I read your book. There are several different types of spirals found in nature.
Yes. If you imagine a coil of rope and you wanted to put it on a deck of a ship without tangling, and if you imagine that you start off with the end of the rope and then you just fold it around itself and to make a little circle, and then you fold the next length around that, and then around that and around that, you get this ever increasing spiral, and that's known as an Archimedes spiral. And another kind of spiral that you find lots in seashells is a logarithmic spiral. And in that spiral, if you think of a nautilus shell, which are those beautiful cephalopod shells that just have the classic, perfect, aesthetically pleasing spiral, again, beautiful, where you start off with a little coil. As you go round the arc of the coil, it splays out further and further and further, and until you get a much wider section, as it were, towards the mouth. And the advantage of that is that the nautilus is a cephalopod, but it secretes its shell on the outside of its body. And the shell is the protection. And in order for this animal to grow, it needs to grow its body in exactly the same proportion as the shell covering. And so the two have to keep pace with each other, and the only way you can do that, because there's a problem with growth, and that is that as you grow, your volume increases much more quickly than your surface area. And of course, they're building a shell which is surface area, but the surface area is required to enclose a volume, and their volume, as they grow, they get bigger. And the only way to accommodate that is with a logarithmic spiral, which gets bigger as you grow, and it keeps pace perfectly in that sense. It's one of these weird things, and very important in nature for things to grow into without changing shape, because the form of a creature matters enormous amount to its function. A bird flying with wings, the wings need to be a certain size, wingspan, in order to be able to create enough lift.
The physics of our world limit this too, right? I mean, like this, and you write about this. There's a great example that you use early in the book about how size impacts function in our world. Like a flea can jump really high, and it could, like, in relative terms, it could jump over the Empire State Building, but a flea could not actually jump over the Empire State Building. And even if it was the size of an elephant. And in fact, if it was the size of an elephant, it could not exist because the physical laws of our universe would just not allow it to. But life often finds interesting ways of skirting around these laws, like not violating them, but just evolving to deal with them and still do something. A great example of that is one of my favorite animals, which I was so happy to see you include in your book, the fairy fly, which is like this fleck of dust and probably should be blown around like a fleck of dust, but its wings are special. Can you talk about that?
Yes, yes, yes. So fairy flies are the smallest flying creature. And I mean, these things are so small that you cannot believe that this thing is an animal. If you think about an animal, what does an animal need to have? It needs to have a nervous system. It's usually got eyes and it's got legs or, something for locomotion. And an animal usually breeds as well, and you've got all of these things in this creature, including wings, and it can fly. And this thing is the size of a full stop. In fact, it's smaller than a full stop on a sentence. So if you took a 12-point
that's a period for the Americans who are
a period, if you take a 12-point font. So next time you're typing something on Word, just do a 12-point font and then just do a period at the end of the sentence. The fairy fly fits inside that period. And it's got wings, but the wings are not like the wings that you imagine on on an airplane for a start, or a bird. And that is that the wings of the fairy fly are almost not there. There's a rod, and then there's little hairs, or there's a tiny, much reduced flat plate with hairs. But the bristles, are what makes them able to fly the way that they do. Because, of course, to something so small, the air is not thin and easy to move through like you or I find. In fact, we don't even notice that the air is there unless it's a howling gale or something. But for the fairy fly, the wind is like the air is like treacle, molasses, and to move through it is hard work. And in order to beat their wing and not have a big mass of air stuck to the wing, which of course would make the wing inoperable, they make the wing porous. So it's got bristles, so most of the air can pass through the bristles, and the wing can make its stroke and create the forces required to flap and have some sort of directionality. Because of course, even if you can fly, the wind is going to take you places that you might not initially have wanted to be.
Your book also includes a really beautiful section on flow, the movement of one substance through another, and that can be, the veins in our bodies, the vascular structure of plants, the way photosynthetic chemicals move through seaweed. This section also surprised me because right in the middle of it, there's this photograph of a zebra. The pelt of a zebra is sort of blurry and beautiful. And I was just stopped in my tracks because I didn't get how this related to flow, right? Like I got flow, I understand flow, and then zebra. And so I had to read the description, which discusses how stripes and spots might form as the result of the diffusion of two or more morphogens through an animal's developing body. And all of a sudden, wow, that's flow. Fascinating. I mean, like, great. Like, how did you think to make that inclusion when you're like choosing? I was like, oh, I've got this beautiful photo of a zebra, which could be used in many different ways in the different sections of this book. But flow was what you chose because of how those stripes get there.
Yeah. So we've got Alan Turing to thank for that, the father of computing, and he pondered how zebras get their stripes and other patterns on the coats of animals, and I mean, he didn't elucidate it completely, but he came up with some pretty good ideas that science has followed. And it's still a very, very complicated area of morphogenesis, the study of the formation of structures and patterns. And there's still a huge amount of things that we don't understand, but it does seem that there is some kind of tension between signals having to diffuse or migrate through material. If you take a glass of water and you put a drop of ink in it, the ink will start moving by diffusion and make up all sorts of interesting patterns. But in an animal developing, in order to control where things are, you want to be able to stop some things moving and allow or encourage other parts moving or developing, and that's done by way of agonistic sort of chemicals and antagonistic chemicals. So it's literally the flow of messages, if you like, through materials in very specific ways. And it's not just the pelts of animals or the wings of butterflies, those beautiful eye spots and things that you see are similarly developed. But plants are hugely influenced by the flow of growth hormones.
Another section of this book is dedicated to color. Color has always fascinated me. I think a lot of people think about it in these terms, although I can't say it in any better way than the lyricist Tim Minchin did in the musical Matilda. And I will refrain from singing this here,
Oh,
but
go on.
but the line is, that when I say red, for example, there's no way of knowing if red means the same thing in your head as red means in my head when someone says red. And this is certainly true all over the world. Colors don't just look different to different creatures. They play different functions, but then they show up again and again with similar patterns as well.
Yeah, I mean, color is just one of these miracles of nature as well, isn't it? There are two kinds of colors. You've got structural colors, which are actually colorless, and I'll come on to them in a sec. And then you've got the normal color the typical color that people think of is pigments. And the thing about a pigment is that the pigment that you see as red is red because the actual pigment is absorbing all wavelengths except red, and the red is reflected, and your eyes pick up the red. And of course, it could look slightly different to you compared to myself because I mean everybody's eyes are different. Some people have to wear glasses, other people don't. Of course, if that red being reflected from the flower pigment, for example, is absorbed by your eye slightly differently to my eye, then it's going to make a slightly different impression. But usually we all know what red is, and it's the absence of all those other wavelengths, like green and blue and yellow. And so lots of animals color themselves with pigments, but you won't ever see a green mammal, okay? Because mammals can't make green as a pigment. So when you bash yourself and you bruise, you might see sort of horrible blues, and you do see greenish. That's about the closest you get to green as a pigment. And then, of course, people that say to me, "Oh, well, then you've got the sloth. Well, that's green. It's got green fur, yes. Well, not
No, but
really.
that's algae, isn't it?
It's algae. That's
Yeah.
right." And so that's an interesting aside is the fact that there are no green mammals. Um, but for other animals can make the green pigment for various biochemical reasons. But the other very important color mechanism is structural colors. And that's where, if you think of a butterfly and its scales, then the scale is a hard material, keratin like. material, and it can have a microstructure, a little bit like the diatoms, if you remember, where they've got a microarchitecture. So the scales of a butterfly can have a microarchitecture, and it's on such a level. It's a nano level. It's nanometers size. Really, I mean, even a very powerful electron microscope has difficulty seeing some of these structures, but they're on the scale of the wavelengths of light. And so when light hits these scales and the microarchitecture in the scales, you get a beautiful play of light, of interference between the various layers that are created by on that scale. And morpho butterflies come to mind as being the perfect example of that, where you just get this like we were talking earlier on about how green an iguana can be. It's just like impossibly green, and a morpho butterfly is impossibly blue, mainly because it's a structural color. And of course, the thing about a structural color is that it doesn't fade. It's a structure, and so the pigments don't fade because of ultraviolet light or anything like that, and they last forever, effectively. And even in the tombs of the Egyptians, there are beetles that are scarab beetles that have beautiful structural color, elytra, the covering of their wings, beautiful, spectacular green of them. They were so spectacular they were used as jewels, and of course they were put with the kings and the queens of Egypt when they died. And they're as bright today as they were the day that they were entombed thousands of years ago.
The idea of color as structure is just like another one of these mind-blowing concepts. We tend to think of it as something that, is layered on top of things or is part of a chemical that will degrade over time. But let's talk a little bit more about structure, because you also have a section on skeletons. We're not just blobs, and nothing really is just a blob. Even things that we think is kind of blob like. You write fondly about an octopus you once met. It's kind of blob like, but we've all devised these different ways of having structure in this world, and that turns out to be really important. And again, also it sort of turns out to be a source of great aesthetic beauty many times.
Yes, yeah. The octopus to which you're referring was a wonderful encounter I had in South Africa, and it was pretty well the first octopus. I was snorkeling, and it's the first octopus that I've been able to sort of observe doing its octopusy thing. And it was hunting crabs, but the crabs were out of the water because the crabs knew that the octopus was there, because crabs are not silly either, and they've got very, very good vision. So they were clinging to the rocks just above the waterline, and the octopus knew this because, of course, octopuses are also very clever. And this octopus would get to the surface and very, very slowly just flick its one of its tentacles out to sense, pick where a crab was, and if it got lucky, it would cast this tentacle out like a fly fisherman casts a line. And if it landed on the crab's back, then that was often curtains for the crab, because of course the octopus was then attached to the crab with its suckers, and it would haul itself out of the water. And now an octopus is not such an elegant creature because it literally turns into a sort of sack of water, like a balloon filled with water. It's sort of a bit wobbly, and its shape is very variable, and that's because of gravity. And it doesn't have any hard sort of skeletal material involved in maintaining its form. But that doesn't stop it from being able. It actually puts that to its own advantage, because it can crawl over a very irregular space, get through very, very tight spaces as well, squeeze its body into gaps on the pursuit of these crabs. But once it drags the crab into the water, of course, then it comes into its own, and it can envelope the crab and eat it. And lots of animals, in fact, for certainly animals coming out of the water onto land, the big problem that they have is gravity, and it's one of the reasons why you don't see animals as the size of whales. The dinosaurs are certainly very impressive, but they're not nearly as big as a blue whale, and they pay the price of being large because their skeletons have to be hugely enlarged in order to support the excess weight. And so that conflict between supporting yourself against gravity on land, the fact that you need to have much disproportionately bigger bones to support that weight, limits the size that life can get on land. Whereas in water, they don't have that problem because the water supports the body. So the blue whale can be 100 feet long, and weigh 150 tons. But as far as we know, dinosaurs never did quite get to that stage.
The way that you talk about all of these things, like the reverence that you have for the natural world is so clear, and the beauty you find in it repeatedly in different ways is so clear. So I wanted to get back to this idea of beauty because I've always sort of thought of beauty as something that is uniquely human, and that even if perhaps other creatures had a similar sense that something could be beautiful, like the peacock, the peahen that you spoke of earlier, that concept would be so much different from ours. But then as I was moving through your book, I began to wonder how you think about this, because if nature creates forms and shapes and colors again and again, repeatable patterns that show up here and there and everywhere, evolving into similar structures with similar purposes, even when they're not necessarily from a similar ancestor, then I wonder, and I wonder if you wonder, if the things we perceive as beautiful perhaps get perceived that way by the other things that we share this planet with as well.
The picture that you mentioned that of the black macaque, and it came up to me and it peered into my camera, and I took the photograph that's in the book of its eyes. When you lock eyes with another animal, particularly like a monkey or an ape, and even lower animals. I've had this experience with all sorts of animals. There's no reason. Often there's no reason for them to come and be with me. And I think my distinct feeling is that things are fascinated by other things. They are attracted by novelty, by strangeness, and I think that, I mean, animals can be scared of other animals, and it's obvious they have to be, because the other animal might well want to eat them. But it's incredible how interested other animals are in us as a species, and in things around them in nature. I've watched the macaques just playing. I mean, playing is a form of expression of beauty, I think. You see something that creates some kind of impression in your mind, and you interact with it. And isn't that what we do when we see something that's beautiful? And I think I do see that kind of thing happen in animals.
That's David Maitland. He is a zoologist, a photographer, and the author of The Shape of Nature, The Intricate Patterns of Life, which you can find at or order from your local bookseller. David Maitland, thank you.
Thank you.
UnDisciplined is a production of Utah Public Radio, and if you happen to live in Utah, you can listen to us on UPR every Thursday morning at 10:30. If you're not in Utah, you can still listen to us every episode, wherever you get your podcasts. Public radio stations around the country have had a substantial cut to funding, so now more than ever, It's important to support this work if you are able. You can do that at donate.nprstations.org/UPR. Our producer is Reagan Edelman. Our theme music is Little Idea by Benjamin Tissot. And I'm Matthew LaPlante. Thanks for listening. Now go have big ideas.